All right, so I'm going to be discussing solutions A through D of this educational round. So I would have done this. Actually, did this video before the editorials came out, but then the file just was nowhere to be found. Apparently, unfortunately. So basically, long story short, I wasted 1 hour of my time recording a video that wasn't even. So I have to basically record again. But maybe it's not a waste of time. We're gonna talk about these problems, and yeah, the ratings are luckily not out. I think so. I can predict the ratings. I guess. So my rating prediction is A is an 800, B is an 800, C is dude low key. I'm stuck between 1300 or 1400. I felt like it was a little. The greedy was somewhat tricky, but it wasn't that bad. Like you just need to look at a test case and you get it, or maybe you're just fours and you don't need to look at test cases. Should I go with 1300? I don't want to second one. I know it's not going to be a 1500. No way. I'm gonna go with a. Oh, okay. 4,000 people solved it. That's vibing with a 1300. Okay, screw it. I'm going with 1300. D. I've done too many 1700s. I know D is a 1700. Mark. Wait, could it be it could be an 1800. No, it's a 1700. D is a 1700. D is a 1700. So we have 800, 800, 1300 and 1700. Boom. That's my rating. I don't know about ENF. I'm too not good. I'm too bad. So what did I say? To solve these problems. Or to even up solve them, I guess. Yeah. So we're gonna go over the first problem, problem A, forbidden integer. I thought this question was trickier than B. B was definitely an easier implementation. This is annoying because you have to deal with the little bit of edge cases and small cases. Just a little bit of annoying stuff, but you'll see what I'm talking about. The problem is pretty straightforward. You just want to sum up. You want to find a way to partition n, and you cannot use the number x, and the only numbers you're allowed to have is 1 to k. So obviously this is always guaranteed to work. Um, and you can just look at the test cases to really get an idea of what to do. For the first test case, we have n is 10, so we're trying to partition n, right? And the numbers we can use are 1 to 3, but we cannot use x, and x is k is 3, and x is 2, so we can't use 2. So basically, the only numbers we can use in this test case is 1 and 3 can be partition n. Well, in this case, you should look at the sample. They partition it in they partition 10 in 3 1 1 1 1 3. Yeah, this is a partition that works. But you sort of want a more consistent one, like so you can actually code it. Like this is sort of random. If you can only use ones and threes, and you're trying to sum this up to 10, a really, really, really obvious thing that should just like be really obvious to you right now is why can't you just spam a bunch of ones? Just spam a bunch, just spam 10 ones, and that works. So we already have a solution if x is not equal 1. So if x is not equal 1, we will just spam n ones. Now it gets a little bit tricky if x equals 1, but luckily this problem, again, problem A, they're not trying to do any evil things. They're just doing a straightforward question. They give you some test cases that actually use ones. So for example, we look at the next test case. We see that um, n is 2 and we cannot use 1, and we're trying to partition 5. If we can only use 2s, then obviously we can't um, only use even numbers to make an odd number, so that's clearly no. And then if we look at the second test case, it actually gives us an insight on how to deal with when x is 1 and when n is even. In this case, we cannot use 1, but if n is even, we can and k is at least 2. Um, then we can basically just spam twos until it works. Spam n over two twos, and then the most tricky one, I guess, is um, again for 773. The next one, x is not 1, so we can just spam 7 ones. And but for the last one, 611, if x is 1 but k is also 1, it's basically saying that we can't use any numbers at all, because the range is from 1 to 1, but we can't use 1, so therefore it's always going to be no. So the tricky part remains is that when x is not equal to 1, k is greater than 1, and we're trying to get an odd number. So for instance, we might have something like 7, um, 3, um, and yeah, 7, 3, and we might have something like 1, when x is equal to 1. In this case, what we can do is we can really do the same case that we did for the even ones. We can spam a bunch of 2's, um, and we can just place a 1 here. But then again, we can't use 1, so we can collapse the last 2 with the 1 to make it into a 3. So in general, for any odd number, if k is at least 3, basically, if k is at least 3, then what we can do is we can just spam a bunch of 2's and collapse, and then spam a 1 and then collapse the last 1 and 2 into a 3, since we know we can't use 1. And the idea is that for odd numbers, um, for odd n, we will always need k to be at least 3, because if k is 2, um, well, then we can't only use even numbers. And we're assuming x is 1, by the way. So that's clearly the case. So we can look at the code. It's pretty straightforward. If x is not equal to 1, we spam a bunch of 1's. That already takes care of half of it. But if k is equal to 1, it's basically saying that since we're assuming x is equal to 1, it's basically saying that we can't use any numbers. So we print out no. And if n is even, we can straightforwardly print out n over 2 2's. If and then now we're assuming n is odd. If k is equal to 2, basically we can't use 1, and so we can only use 2's. Then the answer is no. There's no way. We will need at least 1 3. We need at least one odd number. Otherwise, it's always possible, because what we can do is for 7, we can use n over 2, where n over 2 is the floor, minus 1 2's in general, right? So 7 over 2 is 3, the floor, minus 1. We use 2 2's. We can just spam those 2's, and then we can just use 1 3, and then the answer will be yes. So the idea is that for the most tricky case, we just take the even case, and we just collapse the last 2 and 1. So again, the way you solve this is you could just literally look at the test cases. And they pretty much give you insight on how to solve this problem. It really isn't that tricky. If you just look at the test cases, they pretty much give you some of the cases too. They expose that there. So now we'll look at problem B. I thought this was easier than A though. Basically, what's going on in this question is we have some point, and we start on some point. So maybe I'll do this point in like blue, and the idea is that we want to see how many, like we know there's the shortest Manhattan distance. You can search that up if you don't know what that means, but basically by only going like right in like just regular directions, like right, down, right, left, up, and down. We want to find like the shortest distance. We can't walk diagonally, by the way, or specify that. And the idea is that we want to see how many points coincide in both directions. And you can read the question; it's really straightforward. But the really obvious thing is that if first we break this down into the horizontal and vertical components. If you look at the horizontal components, if they walk in different directions, then no points will ever coincide. So if they start here, but they need to walk horizontally in different directions, no points will obviously coincide. And this extends for the vertical argument too. If they walk in different directions vertically, then no points will coincide. So we only want to consider cases in which they walk in the same direction for the x and the y. And the amount of points that they coincide, for example, if you go vertically, is clearly just the minimum delta between the final position and the initial position, right? Because obviously these are all the points that coincide. And you can just take a look at the code. It's pretty straightforward. Let delta ax be basically the initial position, which is going to be ax. They both start at something, and you just want to see how far they have to go to get to the final position. And yeah, this is just all the deltas. And basically, the main thing is if they are going in the same direction, then we can just add the minimum of them, um, of the magnitudes. Obviously, we only care about the magnitudes because we're trying to see how many points coincide. If they're going, and then we extend the same argument for the y. If they're going in the same direction vertically, we have the minimum of them. And then if you run this in the code, you'll realize that you need to add one. Don't really worry about that nuance. Just add one. It's just a detail you don't really have to worry about. But yeah, this is the same idea. Is that's really pretty obvious. I really don't see how you would not get this problem um, if you had 2 hours to do it. Because yeah, it's just okay. Let me not say that. That might make people feel bad who didn't get this problem. But yeah, it should be straightforward because yeah, if you just walk in different directions, of course you won't coincide at any point. So I don't think any crazy observations had to be made here. C was harder though. C is basically like you're given a strong data or you're given a password database, and the idea is you don't want the password you choose. So basically, what I can show you is we basically what this question is saying is we're given this, and again, this test gets really helped if you solve this question and understand it. Basically, you're given like ranges, and what you have to do is you have to go through each range, and you have to pick a digit between that range. And for example, for each range, which is like a vertical column, we'll pick maybe a digit in between that range, inclusive. So it can be 333. And we want to make sure that this is not a subsequence of this string over here. And this just represents how many ranges we have. Um, and so in this case, if we pick 333, it will actually be a subsequence. So we consider this not a strong password. So we print out no. And it turns out if you try every combination, there should be 4 cubed, 64 of them. All of them will always be a subsequence. And so therefore, um, the answer will be no for this test case. Clearly, we can't obviously try every single combination because that would be 10 to the 10. And then we have to also check if it's a subsequence. So we have to check if the indices are increasing, sort of. So obviously that brute force way isn't going to work. But a very straightforward way to sort of answer this problem is to sort of ask yourself, okay, if I had to go through each range, which number would mi- uh, maximize the chance that I am not a subsequence, or in other words, minimize the chance right now that I am not a subsequence of this string. So it's sort of this sort of greedy idea where we're always picking the best decision to minimize the chance that we are a subsequence in this in this string. And so here you can just try all the possibilities. Let's say if I pick one, then I'll have two, three, four, and 1, 2, 3, 4, 1, 2, 3, 4. I'll have this left. Then the idea is that the next time I pick if I go in the next range, it should be very obvious that you always want to pick a number that is actually initially. So initially, what we want to do, like I think this is what I should say. Initially, what we do in the first range, we want to really pick a number in this range that is not in the string. Because if you can pick a number that is not in the string, then it will never be a subsequence. Think about this logically. A subsequence only contains digits in the string, obviously. And so if in one of these ranges we can pick a digit that is actually not in the string, then it will always be a strong password. So that case is very trivial. It'll always be yes. Um, so in this case, the first range, we can't do that. So which digit should we choose? Should we choose 1, 2, 3, or 4? Um, so if we choose 1, then we really need to consider this string. I'll show you why. I'll show you why we need to consider the string. If we choose 2, we really need to only consider this string. 3, 4, 1, 2, 3. Let me basically, and I'll show you why this is true. So the reason why we only need to consider this string now is because and we can sort of throw out the like we can this was a yes like this we can sort of throw out these characters. So basically like the prefix around the thing we're starting, you can sort of throw those out. The reason why we can do this is because we know if I pick a digit that sort of um is in the string. We always want to pick digits that are actually outside the string, so it could be a strong password. But if it's in the string, then at least for the first digit, I know I'm starting my subsequence at 1. So um, the idea here is when you go into the next range, you always want to pick a number that is actually not inside this range. So for example, for the next range, we want to look for a digit that is actually not inside this range. In fact, what we want is we want sort of we can organize this into the prefix and suffix. What we want is for the next digit we choose, think about it logically, we want a digit that is actually not inside this range. And the reason we want a digit that's not inside this range is so that the digit can be inside this range. In this case, there's nothing there. Because the idea is that if we can choose a digit that's actually inside this range, that is not in this range, in this case, there's none of them, so this is a bad example to choose. But the idea is that if we can choose a digit that's in this range, then we mess up the order of the subsequence. And so, a good example maybe be like you can, for example, in this case, right? I would really want to choose 4 because it's not in this range, and it might be in this range. And so then I would there'd be no possible way to form a subsequence because the idea is that you always want to choose digits outside the suffix because it will mess up the subsequent. It will mess up the order of the subsequence. Because the subsequence, because this is your start of your subsequence. So you know that so if you start the subsequence at sort of, I guess I'll just control Z back. If you set the subsequences at like 4, 3, 2, 1, you know that this is your subsequence, and your subsequence can only extend rightwards. So it can only digits that will make up the subsequence will only be in the suffix, right? And the idea is that for the next one we choose, we always want to choose something that's outside the suffix, so we can not make a so that way we will never be a subsequence of the string. And so the way we do that is, and now it should be very obvious, is we obviously want to choose the number in which the suffix size is as small as possible. Because the idea is that if a digit is included in this range, it will or if a digit is included in this range, it will obviously be included in that range. There's so you can form instances. There will always be instances for every digit that's included in that range. There will always be digits included in this range, but the reverse is not true. There could be some digit included in this range that is not included in that range. In other words, a smaller size suffix has a higher chance that you find some digit not included into the suffix because the prefix is larger. So because you really want digits in the prefix, and so in that case, you want to make your prefix as big as you possible. So in that way, you can find digits that are a part of your prefix, and this will make more sense in the code. I think that basically what I'll let is first index digit I represents the first index of digit in the ith suffix. So in other words, we isolate the ith suffix, and then for some digit, I want to know the first occurrence in that suffix, the index. So what we do, base case, fill out everything to -1, and then this is very, very easy DP. It technically is, but it's very, very easy. You basically can loop through the string to fill this out, loop through all possible suffixes, and then loop through all possible digits. And the idea is that if the digit at the ith position is D, so that's what this is, then obviously the first occurrence is I. Otherwise, it's the last suffix, and it's just the answer is the last suffix, right? So I think that's pretty straightforward. And the idea is that when we go through these ranges, we always want to choose a digit in which this is true. And if we can reach that, then we can return yes. But if we can't reach that, then we know that when I do this, my subsequence can only continue. So if I choose a digit at some position, my subsequence can only continue in the suffix. And so I always want to decrease the size of the suffix, so that way I can always choose a digit outside the suffix. So this condition will be reached. And so the way we do that is we go through all the digits that are in range, and we choose the one that has the maximum index. So that way, the next suffix, so this where the subsequence can continue, will be as small as possible. Because if you want to decrease the size of the suffix, you let it start at a really big index, so that way it's really small. And we do that, and this suffix +1 is to just make sure that you don't actually include the position. Just like you might be wondering, like, we might choose this index or something, but then we know that it's really this suffix that we're talking about. Like this suffix and this prefix, we were not actually including that position. Although you can worry about that when you're coding. I think that's a detail that details are good to worry about. It reinforces um, the problem solving aspect of the problem. And yeah, but that's really it. Yeah, so sort of just asking yourself the idea of what digit would you choose in order to, I guess, always increase the chance that you are not going to be a subsequence. And when you do that, it becomes pretty obvious because once you choose a digit, the subsequence can only continue in that suffix, and so you really want to choose a digit outside that suffix. Now we'll do rating system. So this uses sort of a really nice way to think about prefix sums that I've seen before, for sure. And the idea here is we basically have just a running sum, and if that sum goes below the threshold, then we'll move it up to the threshold. So in other words, the running sum is cannot go below a certain threshold, and we have to find that value in which maximizes the end result of this running sum. And the way we do this is the first observation you have to make is we can think of prefix sums actually as something on a graph. And this is pretty important. And this will actually show you the first observation. So this will actually make sense. So think of prefix sums on a graph. So if we do this example, let's just imagine we don't apply any threshold, because obviously applying a threshold, if you don't apply any threshold, then the answer is just the sum of the array, and obviously applying a threshold is supposed to improve this answer. So let's just think about if we don't apply any threshold to this array, right? So if you don't apply any threshold to this array, it will go up at I think it didn't go up by 1, 2, 3, 4, 5, 6, 7, 8, 9. So the first prefix sum is the empty prefix sum, which is 0. And then it goes up by 5. Um, empty prefix sum 0 goes up by 5. 5, 6, 3, 5, 4, 2, 4. So 0 and then 1 first, 5, and then you have 6. The empty prefix sum is just for edge cases. You'll see. You need sort of that edge case, I guess, but don't think about that too hardly. That's not really the main point of this problem, so I don't care about that detail as much, but that's just for implementation reasons. You'll see. We go down to 4. We go down to 2. We go up to 4. So I guess I'll do this in actually like another color. So you can say that these blue dots represent the prefix sums. And basically, if we apply some threshold, let's say some threshold at, let's just say we arbitrarily say this is some threshold, and this represents the line y equals k, then the first observation should be, it's never, if you're going to, if you, let's say can the optimal threshold be something like this? No, it can't. You can always improve the answer by moving up a threshold to a certain point. Because the idea is that why, like, if you say, like, so you basically know that if I set the threshold here, right? Basically, what I'm saying is that the answer will always be a prefix sum, and the reason why this is true is if you set, let's say you set the threshold here, then after this point, the threshold starts having an effect. Basically, what it means that after this point, this prefix sum is above the threshold. That means we have to get this on the line and this on the line too. So it's basically saying that the threshold actually starts to have an effect, right? It says once it actually goes above the line, so basically once it goes above k, then it actually starts to have an effect. It means that anytime it goes below the line, we actually need to make it at least on the line. Or we have to make it on the line anytime it goes below the line, basically. We have to always make it on the line. And so the idea here is that It's never optimal to place a threshold below a prefix sum because we know that the first point is when this threshold will have an effect when we actually have to start worrying about moving points on the line to make them k that go below the line. And so you can always improve your answer by moving up this line to a prefix sum. I guess a better way to think of this is that think about it like this. At some point, you're adding in elements, a1 plus a2, all the way to some ai. And if you fix the position in which the threshold actually starts to come into play, in which you actually have to start worrying about the running sum going below a, if you fix it at some I, then that means that the prefix sum at I has to obviously be greater than k, because that's when it starts to come into play. But then you might as well say it's always optimal at this point to assign k to the prefix sum as I, because afterwards, for any for afterwards, the impact of a decrease will always be better. The impact of a decrease afterwards, like decreasing the running sum, will always be bounded to a higher position. Like you cannot decrease below this, right? So it's always optimal to have a better threshold, um, a higher threshold at this point I. So the idea is that like if you fix the position where the threshold will come into play, and you said, okay, I'll just say the threshold is k, that this implies that this statement is true. Well, then you can always improve the answer by assigning it to be the prefix sum. So you can just prove this by contradiction. So another way you can think of it like this, and you can sort of just think about when does this threshold come into play, and then it's not really that bad to think that the threshold is always a prefix sum. You can think of this visually, just saying that, well, this is the first point that reaches above the line. Now why not just move it here so that these points can move up higher, and these points can move up higher, and the ending result will move up higher. And so after that, you basically know that the answer is always a prefix sum. And so a very naive solution now is that you can sort of just try each prefix sum and simulate the process, because you try each prefix sum as a threshold, but you don't actually need that. Basically, that if you fix the threshold at some prefix sum, in this case, the optimal one was 6, you basically know that every point that is below this line must move up to k. Like every point must move up to k. Again, we don't care about points that are above the line, they're already good. But any point that is sort of below the line must move up to k. So we know their change has to be the distance to the threshold. This point will have to move. This point will be at this point at this solid line k, and this point will be at this solid line k because now it's below the threshold. That has to be true because that's what's going on here. Is that if you decrease it, it has to. You can just decrease it as much as you can, but it will be set to k. So we know that these points will have to go to k. And the really interesting thing is that if you have to increase this point by this distance in the grand scheme of things, then anytime you increase a prefix sum, it will increase the remaining the prefix sums that come after it by that amount, right? So if you have basically if you have an array and you calculate the prefix sums and you increase this prefix sum to 9, well then obviously this prefix sum also gets increased. If you increase it by 3, this prefix sum also gets increased by 3. So the idea is that basically you'll need that increasing something all the points will be like so first the first thing we need to do is we need to increase this sort of prefix sum to get onto the line, and then that increases this to go over here, but then we know that um, this is not enough because it only increases it over here. And so we know we still have this distance left. So we have to increase it by that distance. But overall, really, if you think about it like this distance, then the last point increased by this. So increased by the distance of the minimum point to the threshold. And so the final result, what they're asking you, if you fix that at some threshold, will basically increase by the minimum prefix sum in that suffix, right? So this is like a suffix, right? The minimum prefix sum, the distance to the minimum prefix sum to the threshold. And the reason why this is true is because think about it like this: for points that are below the threshold, you have to like move them up to the line if they're, and then that will shift all the other prefix sums, and then at any point if it's still below the line, you have to move it up again. But the main idea is that the ending result, you can just observe this, that it'll always move up by the distance to the minimum prefix sum to the threshold. um, Sort of just do a few examples and you'll see that this is always true. This is also a really good example to show why this is true. So just do a few examples, like generate, like, or just make random numbers, and you'll see that this is indeed in true and this is intuitive enough. And so the code is actually very basic here. These problems were actually the implementations. I think actually, funny thing, I thought this implementation is um, easier than problem A, honestly, because really what we're doing is we're just calculating prefix sums, and so you can just do this in one array. And then for min suffix of n or min suffix of I will represent the minimum prefix sum in the I suffix. So basically it's just, do you know how to use the minimum function, right? It's not too difficult. And then we'll just try each prefix sum as a threshold. And we know that the final result will change by this delta, the prefix sum minus the minimum prefix sum. And then if this delta is greater than the max delta so far, we change max delta to delta, and we say that the best threshold is answer, is that prefix sum, and then we just print out the answer. And that is it.